In this video, we'll cover how to process an undirected graph. So to start, let's talk about what an undirected graph is. You can see one here on the left, and really the only difference between an undirected graph and a directed graph is that now your edges can go in both directions. So if we stick with that same example, where our nodes are representing cities, and our edges are representing roads between those cities, an undirected edge is just a two-way street. So as an example, if we look at edge D here, this means that we can go from node 1 or from city 1 to node 4 or city 4. Let's just go ahead and stick with cities and roads to keep things simple. So there is a road that lets us go from city 1 to city 4, and there's a road that lets us go from city 4 to city 1. So we can go in both directions. That's really the only difference of an undirected graph. So if we look at our input format, you can see that it's a little bit different from what we saw in the previous video. Here we have edge A, which tells us, hey, there's the zero node, or this zero city, and the one city that are connected in some way. And that really is a two-directional connection. So it's telling us that we can go from city 0 to city 1, or from city 1 to city 0. Whereas with a directed edge, usually each edge is only telling you one direction that can be traveled. But that is not the case when you're working with an undirected graph. So that's the key difference here. In terms of how we traverse this kind of graph, remember, if we are thinking, hey, we're at city 0 right now, and we want to get to city 5, and we're trying to figure out what is a valid path to do that, well, the first thing we're going to start with is, okay, I'm at city 0, where can I go from here? I can go to city 2, which is kind of useless, it's a dead end, or I can go to city 1, right? So we want to know, given the current node, or current city, which is city 0, where can I go? That's not very easy to figure out, given the input that we have here. So what we want to do is build a hash map, just like we did in the previous video, that will map from a node to all of the other, from a city to all of the other cities we can visit from that current city. Or to put it more generally, it maps from a node to all the other nodes that we can visit from that current node. And we call those nodes children or neighbors. So city 1 and city 2 are children of city 0. You could also say city 1 and city 2 are neighbors of city 0. Okay, so let's go ahead and build out our hash map here. And we're going to do this sort of in a code-oriented way. We're not just going to try to translate this graph into code, but rather let's look at what our input format is going to look like and try to think algorithmically, how can we generate this hash map? So when we go through our edges, the first thing we do is we look at edge A. And here we're going to say, all right, what nodes are we working with? So for now, since we're getting into the code, I'm not going to talk about them as cities and roads. I'll talk about them as nodes and edges, but the concept is the same. Okay, so we have node 1 and node 0 that are connected. So we know that we can go from node 0 to node 1, just like we've seen many times. So we'll say, all right, let's put 0 in here, and we know that we'll put an array, and one of the values will be 1. But, and this is the key piece that people mess up with undirected edges, we need to consider the other piece of information that we can figure out from this edge, which is that we also know that from the 1 node, we can get to the 0 node. So the 0 node is actually a neighbor of the 1 node. So we need to record that information as well before we are finished processing edge A. This is the key thing to understand with undirected graphs, is every edge tells you two pieces of information, and you need to handle them accordingly. Okay, that's it for what we have to do with this edge. So we can go ahead and cross off the A edge. I'll do it right next to the letter. So this one's done. Now we go to the B edge. So this is telling us we can go from 0 to 2. So let's add it. 2 here, but it's also telling us that we can go from 2 to 0, so we want to add that. So we're pulling two pieces of information from every single edge. Now we get to edge C. This is telling us that we can go from node 1 to node 3, and from node 3 to node 1. And that covers the C edge. Next we have the D edge. This says that we can go from node 1 to node 4, and then from node 4 to node 1. So that covers the D edge. Now we have the E edge, which says that we can go from node 3 to node 5, and from node 5 to node 3. That's it for the E edge. And lastly, we have the F edge, which says that we can go from node 4 to node 5 and from node 5 to node 4. And this is all. We can go ahead and check off the F. We have now processed all of our edges from the input, and we've built this hash map that allows us to easily walk through the graph that we have on the left. And this way, if we are at node 0 or city 0, now we can go back to thinking about it as a city. If we're at city 0 and we want to get to city 5, we can ask that first question, which is, where can I go from here? We'll go to our hash map and we'll realize, oh, we can go to city 1 or city 2. And then we'll figure out, all right, which of those two paths makes sense? Well, from city 1, I can go to city 3, and then from city 3, I can go to city 5. So that is a valid path, and it's much quicker to find that solution when we have this hash map that we can build in the beginning. All right, the last thing I want to talk about before we jump into the code is the complexity of what we're doing here. So on the right, we can go ahead and write out complexity, and the first thing we'll do is define our variables. So in this case, our input is going to be a bunch of edges. So let's say E is going to be the number of edges we have. Now, what did we really do here if we want to think a little bit more algorithmically about what we did? We just really iterated through every single one of these edges and then stored two pieces of information in our graph for every single edge. So that's like, O of 2E work that we're doing, which just comes down to O of E work. So our time complexity is going to be O of E, because we're just iterating through our edges and then doing constant work for each edge. And our space complexity is going to be the same thing, is also O of E. The reason is because what we are storing here depends on how many edges we have. As an example, like these two edges here, the ones like 0 to 1 and then 1 to 0, come from this A, and so on. So the more edges we have, the more pairs we're going to have to store in our graph. Or the easiest way to think about it is, what would our hash map look like if we had 0 edges in the input? Well, we would have an empty hash map, right? So you can see that the number of edges is determining the size of this hash map. Okay, that's all for the approach. Let's go ahead and jump into the implementation to see what this looks like in code. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've copied over the input that we saw in the approach and the desired output that we were able to generate. Before we actually solve this question, let's go ahead and figure out how we're going to test it. So we're going to have a graph that will be built by calling our function. Let's say we'll call our function process undirected graph here, and we'll have to pass some arguments, right? Because we need the input. So let's say we'll have our edges, which will just be this example input for now. And we're going to pass edges in here. And then let's just say we want to print out our graph to make sure that we successfully solved the question. Okay, great. So now we have that working. Let's write our function. So it's going to take in edges and we want to do something with it. Now we know that our output should be a hash map, which means in JavaScript we want to be using an object. So let's go ahead and define our graph to be an object, and let's return that in the end. Now the question becomes, how do we fill the object? And if we think back to what we did in the approach, we were certainly iterating over all the edges. So let's start by doing that. We'll use a for each loop here. So we'll just pass a callback function that says, hey, what do we do for every edge? Now for each edge, you want to figure out what two nodes is it dealing with. So I'm going to use some destructuring here. So let's grab node 1 and node 2. Notice that I'm not calling them start and end, because this is not really starting at 0 and ending at 1. It goes both directions. So we'll keep it more generic like this. Now, remember there are two pieces of information that we need to record in our hash map for every single node. We want to say that node 1 can go to node 2, and node 2 can go to node 1. So in our first edge, as an example, we want to say that we can go from 0 to 1, but also that we can go from 1 to 0. So let's say, all right, if we want to go to our graph and we go to node 1, so if we're at the 0 node, you're saying, hey, go to this right here and get this array. I want you to push into it node 2, which means we're saying take this node and push it into the array. And then we have to do the reverse direction, which is saying go to graph at node 2. So take 1, find that in our graph right here. So it's this array. And then I want you to push into it this value of 0. So what we're going to push here is going to be node 1. Okay, this is really the core of what we're doing in this question. The only piece that's missing is how do we actually create these arrays here? And that's pretty straightforward. We can just handle that by saying if we don't already have a value for the key that we're worried about, just put an empty array there. So we can just say if not graph at node 1, then graph at node 1 should be an empty array so that we can use push properly later. And similarly, we'll do the same thing for node 2. So we'll say if node 2 doesn't exist in our graph, then we'll say make graph at node 2 be an empty array. Okay, that is the core of how this algorithm works. I just saved and prettier reformatted this, but it's the same code as before. It's just formatted a little differently. All right, so now we can go ahead and test this, and then we'll talk about the complexity. So the output we can compare. So let's run this. Okay, so we got our output. So we have 0 through 5. We know we want that. We have 1, 2, 0, 3, 4. Let's compare. 1, 2, 0, 3, 4. And then we have 0, 1, 5, 1, 5, 3, 4. 0, 1, 5, 1, 5, 3, 4. Okay, fantastic. Looks like our code works correctly. Now, I want to talk about the complexity of this so that we can kind of look at the code and analyze where that complexity comes from, not just from the approach, but also from the code. Okay, so our time complexity is O of E, and our space complexity, space is O of E. Now, the time complexity, I think, should be not too difficult to figure out when you're looking at the code. These 2 lines of code here just happen in constant time. This is what determines your time complexity. Clearly, we're going to be O of E because we're iterating through every edge. Then the question becomes, at each iteration, how much work are we doing? Well, destructuring is constant time. These 2 conditional statements are constant time, and pushing happens in constant time in JavaScript. So overall, we have O of E time that is primarily determined by this line right here. In terms of space, you can see the same thing, because for every edge, we add 2 entries to the graph. So the more edges there are, the larger our graph is going to be. And if we have 0 edges, well, then our graph is going to be empty. So that covers why the time and space complexity are O of E. Both of them are. That's all for this video, and I'll see you in the next one.